Let's conclude this chapter by looking at high-frequency monsoon variability for both the summer and winter monsoons. High frequency here essentially refers to the synoptic scale day 1 to 10. Typically day 3 to 10 is what is mentioned as synoptic scale, and they are these northwestward propagating low pressure systems or monsoon depressions. There are definitions associated with their pressure drop, the speeds, winds associated with them, and so on. And the main point from this figure from Goswami et al. 2003, as presented in the book chapter, the interseasonal variability by Bill Lau and Dwayne Walliser that I mentioned before, and the heavy modulation of the high frequency variability by the meso or the ISO phase, interseasonal ISO phase, is shown here. This is the strong active period, and you can see almost all of the origins of the monsoon depressions or low pressure systems are happening over here in the northern bay, with a few over here, and they all trek across into the core monsoon zone and bring a significant amount of rain onto the seasonal total. Whereas during the break period where the central core monsoon zone is experiencing a mini break or mini drought, as it is often referred to, there are far fewer low pressure systems and not as well organized. They're distributed all over and even on the Arabian Sea side. So obviously there is interactions with the background states which are associated with the active and the break phases. So the question then is, what is the perturbation that can trigger these low pressure systems? We jump straight to the mid-latitude potential vorticity intrusions again, but this time look at a synoptic time scale. So this is the 370 Kelvin upper atmosphere isentropic potential vorticity that we have already looked at several times, but now we will look at a few days. So this is just going from 13th June to 25th June, a couple of weeks, and we have our typical meandering potential vorticity substance that we had looked at, and its intrusion into the tropics in the westerly duct or in the winter months through the upper tropospheric trough. And you can see the breaking the filaments, the signatures of the recursive Rossby waves that intrude and then are trekking across, propagating across into the Atlantic sector. And over time you can see the disturbances being caused over the region of the Bay of Bengal, where the monsoon depressions form. And remembering that these are in the upper atmosphere, then you need to relate them to the lower atmosphere, where the monsoon depressions are bringing moisture and rainfall. There are also ideas that it's the rainfall and surface perturbations that can generate upper tropospheric quasi-biweekly timescales and other high-frequency timescales. So essentially we're still kind of in the hypothesis stage of these things, but if you can look in the 10 to 30 day timescale, the change in potential vorticity instead of the total potential vorticity for the same days from the seasonal mean, for example. And you can see the wavy pattern here, the intrusions here, the westward propagation here, and the changes delta PV occurring in the box here, or the 370 Kelvin isentrope, right? So, and you can see the phase change as well on these quasi-biweekly time scales. So within this week it has gone from negative to positive. So that's not always so obvious when you look at the totals. So when you bandpass filter, it becomes more obvious, and those are seen as indicators of extratropical forcing of the these synoptic events that we are talking about. So this is the evolution of the isentropic PV field and its 10 to the 30 anomalies that we looked at before, but going a few more days here so we were at 25th June and now we are into 28th June, but you can see the full cycle in terms of the genesis region of this monsoon depressions, the Western Arabian Sea, Eastern Arabian Sea, and the Bay of Bengal. So does that explain the genesis? Not exactly, but at least it's a hint that extratropical perturbations may be part of the dynamics. This is showing Hofmüller diagrams of the same 370K isentropic potential vorticity, but now we are looking at various latitude bands. To the north of the Bay of Bengal, 25 north to 35 north, and in the middle, 15 north to 25 north, essentially over the Indian monsoon zone, and 5 north to 15 north, which is about the tip of the peninsula into the middle of the peninsula. But time going up here, so May, June, July, this way, and you can see this is going from the Atlantic Ocean into the Pacific Ocean, Eastern Pacific, and back into the Atlantic Ocean. So you can see these propagating features associated with the same features that we are seeing here. We are taking sections as latitudinal averages, but the direction of propagation, so we have the propagation in the westerly jet part in the northern band that we are looking at, and when you come down into the monsoon zone you can see the eastward, so you have to go up in time, so eastward propagation and westward propagation, and similar westward propagation is seen also in the 5 to 15 north band, basically corresponding to these features. So you have eastward propagation here and then westward propagation in these bands over the monsoon and over peninsular India. So that again is a implicit argument that extratropical PV intrusions and their navigation around the Asian monsoon gyre that we talked about, that sits over the Himalayan Tibetan plateau. So this circulation around, so the impact of the Asian monsoon gyre is pretty large in terms of steering the potential vorticity intrusions around it and creating wave breaking and filaments and potentially generating these perturbations. Similar things happen in the winter monsoon as well. We have already talked about the winter surges. We also talked about the easterly jet and the acceleration of the geostrophic flow within it that introduces a geostrophic component in the total velocity field. So now we are looking at the XY plane, but looking at the westerly jet, which also has this squeezing of the isotherms, divergence and convergence bands. You can think of also as pressure. So this is going from latitude of phi plus delta phi around phi to phi minus delta phi. So you have convergence on this side, divergence on this side, like before. We have the acceleration happening of the geostrophic flow, which we saw is going to introduce the ageostrophic flow. Acceleration part here is going to introduce the northward ageostrophic flow here. Coming out here, you're going to have deceleration, which is going to introduce a southward ageostrophic flow. And those are associated with the winter surges, as we will see in a minute. So that looking at A, B, and C, D sections like before, you have a circulation around the westerly jet, secondary circulations set up because of these ageostrophic induced flow because of the geostrophic acceleration. So this is in the anticyclonic sense, and this is in the cyclonic sense. So you have rise and fall, and rise and fall happening in this kind of circulation. So you are setting up secondary circulations to adjust to this ageostrophic induced meridional cells. Okay, very similar to before, but these are going to be now associated with setups of winter surges. So you can see that there is the trough that we are talking about, which moves during the surge and squeezes the jet and creates these northward and southward ageostrophic components as the air parcel is accelerating geostrophically through this squeezed streamlines, and you can see the surge, the jet getting stronger, and the trough over that is creating these stronger ageostrophic induced circulations. So the isolobars, which are not just isobars, those are pressure surfaces that are changing by the same amount over time. They are called isolobars. So you can see a change of -5 +5. So you have V tilde being 0 in the middle and inducing ageostrophic flow, geostrophic acceleration, and that's the total flow here. And you can see the another situation here where you have a very strong pressure drop, high pressure on the other side, and you have a winter surge which can come all the way into the tropics. And I have mentioned before that these can be very strong, often associated with various features in the deep tropics, and as I mentioned before, some of the westerly wind bursts are also attributed to these wind surges. I'll keep going. This is the surface zonal wind speed at the IMET buoy in the West Pacific, just south of the equator at 1.5 degrees south for this period during the Toga core, and you can see the clear westerly wind bursts here. So here is the zero line. These are the easterlies and these are the westerlies. These are also in the high frequency band. So they typically last for about 7 days, and the definition is that they have to have wind speeds of over 8 meters per second or so. And you can see these reddish, magenta-ish colors here have wind speeds in the range of over 7 to 15 meters per second, and you can see that they last typically for a week or two. These obviously are large enough in spatial scale, strong enough to set off Kelvin waves, which are then seen in the ocean, in sea level, and in thermocline depth. As they propagate eastward, they are going to push the thermocline down, create warmer SSTs, change the sea surface temperature gradient, and can induce coupled Bjerknes feedbacks that we talked about. So typically 93 from about 91 to 94 there were multiple weak El Niños. So you can see 92, 93 had multiple wind bursts, and you also get a sense that they are multiplicative noise. As I said, they typically start west of the dateline, and as they push the warm waters of the West Pacific warm pool eastward and the convection migrates with it, the westerly wind gusts get stronger and cross the dateline and head towards the East Pacific. So during the strongest El Niños, you see these extending all the way into the Eastern Pacific Ocean. So they are key part of the El Nino dynamics, and we had seen this also before in the Toga core data in terms of Kelvin waves, looking at three locations, the sea level, so this is the eastward transport per unit width in meters squared per second. Nonetheless, there is a sea level signal associated with them as well. So you can see the transport signal here first, and then appearing here after the Kelvin wave timescale. These are not advective timescales, and then you see the signal over here after some more time. So the speeds of 2.52, 2.43, and 2.4 are basically consistent with the eastward Kelvin wave speeds in the ocean. So winter surges, high frequency variabilities, and the summer high frequency variabilities are all potentially related to this extratropical forcing, either as the PV intrusions and wave breaking creating perturbations in the summer months, or the winter surges, especially the very high Siberian high pressure center, anomalously high, creating these waves that we talked about, and the acceleration in the westerly jet, and then the equatorward winter surges. Okay, so that's the high frequency monsoon variability in the summer and winter. That concludes the chapter. Most of the focus has been on South Asian monsoon. We touched on Australian and African monsoons, but obviously South Asian monsoon is the most dramatic of the monsoons and has lots of interesting physics which we touched upon. We'll look at some more details in the next chapter when we look at the coupled monsoon dynamics. Okay.